Welcome to this next video in the playlist on ring theory. In this video what we're going to talk about is Gauss's lemma. Now the first thing to say is that Gauss had a huge number of lemmas. Okay, the one that this video is about is pertaining to polynomials in ring theory. Okay, the second thing to say is that even with this one Gauss's lemma, in ring theory, there are loads of different statements that are all different but are all effectively equivalent. They're all using the same proof strategy to actually prove what they want to prove. Okay, so lots of different authors, however, will call Gauss's lemma different statements. I am going to give you a quite generalized form of Gauss's lemma, which I think is most useful for us discussing ring theory. Okay, but it is far more generalized than the Gauss's lemma that Gauss actually proved. Ours is going to be written in the language of ring theory, which didn't even exist when Gauss lived. Okay, so it is a big generalization of what Gauss originally proved. It's much like Euclidean domains are named after Euclid, even though of course Euclid didn't define what a Euclidean domain was. He worked out the Euclidean algorithm in the integers, and Euclidean domains are a generalization of the integers. They all have a Euclidean algorithm, and the strategy for showing that this gives rise to a greatest common divisor is exactly the same as what Euclid used in the integers. Okay, hence why Euclidean domains are called Euclidean domains. Similarly, this lemma that I'm about to show you, it's called Gauss's lemma because it uses the same proof technique as Gauss originally used in his original, much more specific lemma. Okay, so that's the introductory speech over. Let's now actually see what I'm going to call Gauss's lemma. So we'll start with a statement of Gauss's lemma. Okay, so we're going to be working with a ring which is a unique factorization domain. So let's say R here is a unique factorization domain, a UFD. So that's our starting assumption, that we're working with a unique factorization domain. Okay, and we're going to be asking about polynomials in the ring of polynomials over this unique factorization domain. So let's say we've got a polynomial p of x, which is an element of the ring of polynomials where the coefficients are from this unique factorization domain, which we're calling capital R here. Okay, and let's assume that it's a non-constant polynomial. Okay, an interesting polynomial. So we're assuming that p of x here is a non-constant polynomial. So Gauss's lemma, as I'm going to state it, is all about when this polynomial is going to be reducible. Okay, and Gauss's lemma says that this polynomial will be reducible if it's also reducible in the ring of polynomials over the fraction field for this UFD, capital R here. Okay, so let me take a step back and talk you through this. Okay, so R is a unique factorization domain. All the unique factorization domains are integral domains. They are integral domains with that additional property that all elements can be factored down. Well, all elements are either a unit or they can be factored down into a factorization of irreducibles, which is unique up to the fact that you can change the associates that you're using. Okay? But it is fundamentally an integral domain, and therefore it can be extended up to a fraction field. So for this unique factorization domain R, we can construct a fraction field, which I will throughout this video call F, okay, which will contain R. Okay, so remember, any integral domain is always included in its own fraction field. So R will be a subportion of the fraction field here, a subring of the fraction field. Okay, there's always a nice injective homomorphism that will map the integral domain into the fraction field. And remember what the fraction field is. You construct all fractions, all things of the form a numerator over a denominator, where the numerator and denominator are just elements of the integral domain, but the denominator can't be equal to 0. And then you define those equivalence classes of equivalent fractions. So you partition the set of all fractions into these equivalence classes of fractions, and then it's the equivalence classes of fractions which become the elements of your fraction field, and on which you can define addition and multiplication. Okay, that's just a reminder of fraction fields. We do have a video earlier on in this place on ring theory on fraction fields if you're a little bit rusty on that concept. Okay, so now what we can do, of course, is construct the ring of polynomials over the fraction field here. So f adjoin x is constructible, okay, and of course our polynomial p of x, which is a non-constant polynomial in the ring of polynomials over the initial unique factorization domain R, that will also be a polynomial in the ring of polynomials f adjoin x here. So p of x will be an element of the ring of polynomials over the field capital F, because of course R is included within the fraction field, so all the coefficients of our polynomial p of x, which are in R, are also going to be in the fraction field, so it's perfectly reasonable to say that p of x will be an element of the ring of polynomials over the fraction field here. Okay, and my claim now is that this polynomial p of x, it will be reducible, okay, in the ring of polynomials R adjoin x here, if it is reducible in here. Okay, so if I can show that p of x is reducible in the ring of polynomials over the fraction field, then you can conclude it's reducible in the ring of polynomials over the initial unique factorization domain. Okay, note you do need this to be a unique factorization domain. It can't just be an integral domain that you're working with here, even though of course for an integral domain you can construct a fraction field. Okay, but you do need your starting ring here to be a unique factorization domain. Okay, right, so that is Gauss's lemma. If you want to know whether this polynomial here is reducible in the ring of polynomials over the initial unique factorization domain, construct the fraction field that contains that unique factorization domain. If the polynomial p of x is reducible in the ring of polynomials over the fraction field, then you can conclude it's reducible in the ring of polynomials over the unique factorization domain. That is Gauss's lemma. Okay, so let's set to work with actually proving this. Actually, before I just set to work with the proof of this, let's give obviously one of the main examples, the example that Gauss had in mind when he was actually proving this. Okay, and in fact his initial lemma was with respect to this specific example rather than a general unique factorization domain in its fraction field. Okay, so the famous example would be the ring of integers is a unique factorization domain if we have a polynomial in the ring of polynomials with coefficients in the integers, and we want to know, is it reducible in that ring of polynomials with coefficients in the integers? What we can do is think about it as a polynomial in the ring of polynomials where the coefficients are in the rationals, and of course the rationals is the fraction field for the integers, and then we can ask, is this polynomial reducible in the ring of polynomials over the rationals? And if the answer is yes, then we can conclude that it's reducible back here. Okay, so that's where Gauss's lemma originally came from, just talking about reducibility in the ring of polynomials over the integers. Okay, right, so let's now prove Gauss's lemma, and we're going to prove it more generally. So this is just the specific example, but we're going to prove it for a general unique factorization domain with its fraction field f. Okay, so let's start the proof here then. So, proof of this. Okay, so what we're going to do is we're going to take our non-constant polynomial, okay, p of x. So we'll start off with our polynomial p of x, which is in the ring of polynomials where the coefficients are in the unique factorization domain R here. Okay, and we're now going to look at it as being an element of the ring of polynomials where the coefficients are in the fraction field f. So of course what we can now do is view this as being an element of the ring of polynomials where the coefficients are in the fraction field. And now we're going to say, okay, it's reducible in here. So we're going to assume it is reducible in here. Okay, and what I now want to prove from that is that it's reducible here. Okay, and if I do that, of course, I will have proven Gauss's lemma. Okay, so if it's reducible in the ring of polynomials over the fraction field, what does that mean? Well, by definition, that means that I can write it as a product of two polynomials that are in the ring of polynomials where the coefficients are in the fraction field, and these polynomials are not units. Okay, so let's do this. So p of x can be written as, let's say, a polynomial capital A of x here times another polynomial capital B of x here, where both of these polynomials, both capital A of x and capital B of x, are in the ring of polynomials with coefficients in the fraction field capital F here. Okay, Excellent. And both of these polynomials, both ax and bx here, they will not be units. Okay, otherwise we haven't found you a factorization which actually is the factorization which shows it's reducible. Remember, the definition of reducible is that there must exist a product of two things in your ring which gives that element where neither of them is a unit. Okay, I've supposedly taken one of these products. Okay, so these are not units. It's always possible to find this if this polynomial p of x is indeed reducible in the ring of polynomials over the field capital F. Okay, now what does it mean then if these are not units? Well, of course, because this is a ring of polynomials over a field, then the units are going to be the constant polynomials and only the constant polynomials. The non-constant polynomials will not be units because, of course, a field is an integral domain, and we know in an integral domain non-constant polynomials are never units. Okay, so what we can conclude is that they are not constant, so these are non-constant polynomials. Okay, and what we now want to prove is that from this we can find a factorization in the ring of polynomials over the initial unique factorization domain where the two polynomials are not units. Okay, and in fact the way we're going to do this is we're going to find polynomials which have exactly the same degree as a of x and b of x here. Okay, so we can therefore tell that they will not be unit polynomials over here because this is also an integral domain, and in an integral domain non-constant polynomials are not units. Okay, they cannot be units. So if we can find polynomials of the same degree as these two, but which are in the ring of polynomials over the unique factorization domain and which multiply together to give p of x, then we're done. If they're non-constant, then they will not be units, and therefore we will have found a factorization into two non-unit elements in the ring of polynomials over the unique factorization domain. Okay, so how are we actually going to do this then? Okay, well, we're going to do a reasonably intuitive thing. We're going to get rid of all of the denominators in the coefficients of these two polynomials, capital A of x and capital B of x. Okay, now to make this clearer, it'll probably be good to write out explicitly an explicit expression for A of x and B of x. Okay, so let's do this now. So P of x here, okay, is going to equal A of x times B of x. Now let's come up with an explicit expression then for A of x. Okay, so these polynomials are going to have coefficients from the fraction field. Okay, so their coefficients are going to be fractions. So they're going to have a numerator and a denominator that are in the initial unique factorization domain R. So I'll write it like so. A0 over A0 prime here plus A1 over A1 prime times x plus all the way up to, let's say the degree of A of x here is n, so it'll be an over an prime x to the n here. Okay, where all of these numbers are from the initial unique factorization domain R. So the AIs and the AI primes, they're all elements of the initial unique factorization domain capital R here. Okay, and now we'll also do the same thing for B of x here. Okay, so B of x will also have the same thing. So we'll have B0 over B0 prime plus B1 over B1 prime times x plus all the way up until we have, and now we'll say the degree of capital B of x is m, so we'll have Bm over Bm prime x to the m, like so. Okay, so there's our polynomial B of x, and I'll underline the polynomial B of x here in orange. Okay, and again, all of these numerators and denominators, the BI's and the BI primes, they're all elements of the unique factorization domain R. Okay, now, of course, all of these fractions, really, we should think of them as representatives of their equivalence classes, because the fraction field is actually made up of those equivalence classes of fractions rather than individual fractions. Okay, so be aware of that. Right, okay, so what am I going to do here? What I'd like to do is get rid of the denominators, so what I'm actually going to do is multiply both sides of this equation through by an element of my unique factorization domain, which I'm going to call D, which is going to be all of these denominators multiplied together. So we're going to have A0 prime, A1 prime, A2 prime, all the way up to AN prime here, and then we'll have all of the B denominators here. So we'll have B1, oops, not B1 yet, B0 prime, B1 prime, all the way up to Bm prime here. So I multiply all of the denominators together. Okay, and that's something that I can do in my unique factorization domain R, because they're all just elements of the unique factorization domain R. Okay, so this is perfectly valid to do. Now, what I can be absolutely sure about is that this is not equal to 0. This great big product is not equal to 0, and that's because all of the denominators cannot be equal to 0. Okay, that's a condition that I didn't write here, but we know is true in a fraction field. We insist that the denominators A1 prime, AI prime and Bi prime are not equal to 0. The denominators cannot be equal to 0. Okay, so we've multiplied loads of non-zero things together, and of course we know we're working in an integral domain, so when we multiply those of non-zero things together we get something that is non-zero. Okay, so this is a non-zero element. Okay, now, what I'm going to do then is multiply both sides of the equation by this. Okay, and of course you can just distribute this out. Okay, so if I do this, we'll have d times p of x, and then we'll take this portion, the portion involving the a's here, and we'll stick that in front of this portion. Okay, so we'll now have a d in front of, so if I just write this out, it will be d in front of a of x times b of x here, and I'm going to split d up into the a portion and the b portion. I'm going to put the a portion in front of this portion, and I'll put the b portion in front of the polynomial b of x here. Okay, so I'll give the a portion to the polynomial a of x, obviously, and I'll give the b portion to the polynomial b of x, of course. Okay, and then I'm going to expand out the brackets. So I'll take this and multiply it by the a polynomial here, and of course what I'll get is, when I multiply this with this first term, the a0 prime will cancel with the a0 prime here. Or what you can really think about doing is multiplying this with this, and this, strictly speaking, of course, we should have this over 1, okay, because it should really be a fraction or an equivalence class of fractions, so it should really have over 1 as part of this, but you know, we have enough intuition for how to work with fractions now. Okay, so when we multiply this, of course, this product of all of these a's will multiply and it will become part of the numerator here, but then we can find another equivalent fraction. So to do an example of this, what we'll initially get is a0 prime, a1 prime, all the way up to an prime, multiplied by the a0 on the top there, and then in the denominator you'll have a0 prime, because the denominator of this, strictly speaking, would have been 1. Okay, so 1 multiplied by this would have remained the same. Okay, and now that is in the same equivalence class as the fraction where you've cancelled the a0 prime. So you can cancel off the a0 primes here and get what's left over 1 here. Okay, and that initial element I had where the a0 primes were still there will be in the same equivalence class, so it will be the same element. Okay, and then of course we'll have something with a denominator of 1, and such things have an equivalent element in the initial unique factorization domain which we constructed the fraction field from. Okay, so elements where there's a numerator with a denominator of 1 are those elements which have an element in the original integral domain that corresponds to it. Okay, so effectively what we've done is got rid of all the denominators and turned the numerators now into things that are back in the unique factorization domain, capital R. So I hope you can appreciate that with all of these the denominators will cancel. So in this one the a0 prime will cancel with the a0 prime here, the a1 prime will cancel with the a1 prime here, all the way up to here where the m prime here will cancel with the am prime here, and then in the b polynomial the same thing will happen. b0 prime will cancel with this b0 prime here, b1 prime will cancel with this bit here. Okay, of course you'll get complicated numerators now, but the point is that the denominators of each of these will have gone. Okay, so this should hopefully at least be intuitive in the context of the rationals, and it works in the more general case as well. Okay, right, so what I have now done then is developing this further. I've now got d times p of x is equal to these new polynomials, which I'll call a of x, little a of x, and little b of x. So these new polynomials, little a of x is this thing, all of the denominators from the polynomial capital A of x multiplied with capital A of x, and little b of x is this thing multiplied by capital B of x, basically. Okay, so I think I should just underline this in the same way. So we would multiply, and I'll come up with a colour, we'll have yellow here, this string of the b0 prime, b1 prime, all the way up to the bm primes. We've multiplied that with the polynomial capital B of x here. Okay, so we've now got little a of x and little b of x, and of course these polynomials, little a of x and little b of x here, they are now elements not of my ring of polynomials over the fraction field, but of the ring of polynomials over my initial unique factorization domain. Okay, so R adjoin x. So this is all going rather well. I've now got polynomials here, okay, which, note, will have the same degree as the polynomial capital A of x and the polynomial capital B of x. In particular, they will still be non-constant polynomials, so that's why this is going particularly well. Okay, so they will still be non-units in there, and I've now got them multiplying together to give R. Not quite p of x, but d times p of x. Okay, that's the one problem at the moment. We need to somehow get rid of that d. Okay, that's the one thing that we need to sort out now. We need to get p of x as a product of two polynomials that are not units in order to prove that it is indeed reducible. Okay, so how are we now going to approach this? Well, there are two cases here. Okay, case 1's the easy one, and case 2's the more difficult one. So let's do case 1 firstly. Case 1 is that this element here, d, which is this great big product that I've shown you here of all of the denominators, okay, the case 1 is that d is a unit. If d just happens to be a unit in the initial unique factorization domain R, then we're in luck. Okay, because of course it will have a multiplicative inverse, and we can multiply both sides by the multiplicative inverse, and we'll get that p of x is equal to 1 over d, okay, which is just an element in the unique factorization domain, and therefore also in the ring of polynomials over that unique factorization domain, okay, times this polynomial a of x, and then times the polynomial b of x, like so. Okay, so now you've successfully done what you set out to do, because now we can just say, okay, this polynomial 1 over d times a of x, let's define that to be one of the polynomials that we've got in this product, and then we've got this other polynomial b of x. Okay, both of those will still be non-constant polynomials. They'll still have the same degree as capital A of x and capital B of x respectively, therefore they will be non-constant polynomials. Because the unique factorization domain is an integral domain, then we can be sure that in the ring of polynomials over that unique factorization domain, non-constant polynomials are not units, and therefore we've got two not units multiplying together to give p of x, hence p of x is reducible in the ring of polynomials over the unique factorization domain. End of. Okay, end of proof. The other case is that d is not a unit. That's the easy case. Okay, now case 2, of course, if it's not a unit, we can't just multiply by its multiplicative inverse on both sides. Okay, and case 2 is where we now rely on this being a unique factorization domain. Okay, so you might have been wondering, why do we need it to be a unique factorization domain? Nothing that we've done so far relies on it being a unique factorization domain, but now it's going to rely on it being a unique factorization domain. Okay, so case 2, if d is not a unit, then it's going to have some unique factorization into irreducible. So remember, d is an element of the initial unique factorization domain capital R, okay, and all elements in there that are not units can be factorized into a very nice unique factorization in terms of irreducible. So let's now do that. Okay, so what we can successfully now do is write d as some unit out the front times one irreducible, let's call it p1 to the power of alpha 1, then another irreducible p2 to the power of alpha 2, and it goes on all the way up to, let's say, p, and we'll go up to n, but of course this n isn't meant to be the same as the n that we had up here, it's just I can't be bothered to come up with a new symbol, okay, it's just some arbitrary natural number. Okay, right, so I've factorized it now down into this unique factorization of irreducibles here. And remember, this will be unique up to the fact that you can mess around with which associates of the irreducibles you're using, and you might also have to mess around with what the unit is out the front when you change the associates here. Okay, right, so we can factorize D out into this factorization in terms of irreducibles. Now, what I'm going to show you one by one is that we can get rid of these irreducibles. So currently what we have is that this element here is multiplying the polynomial p of x, okay, and that's giving me this polynomial little a of x times the polynomial little b of x. This is what I currently have, okay, this is where I currently am. Okay, what I want to do is get rid of these one by one. And how am I going to get rid of them? Well, I'm going to have to cancel them, okay? What I would like it to be the case is that I can pull out each one of these irreducibles from this product of a of x times b of x. Okay, so how can I do this? Why can I do this? Well, now we need to show that you can do this. Okay, so this is the clever part of the argument, and it, as I say, completely relies on this now being a unique factorization domain. Okay, so you will remember from the video on unique factorization domains that in a unique factorization domain, irreducible elements are exactly the same as prime elements. Okay, even though the definitions are different, in a unique factorization domain where all elements can be factored in a unique way into a string of irreducibles, you can prove, and indeed we do prove in the video on unique factorization domains, that the two definitions of irreducible and prime become one. Okay, of course, a prime element is always an irreducible element whenever you're working in an integral domain, but if you're working in a unique factorization domain, it also works the other way around, that if you're irreducible, then you are also prime. Okay, so that means that all of these irreducibles here, P1, P2, all the way up to Pn, they're all primes. So that means that when you generate their principal ideal, you get a prime ideal, you get a non-zero prime ideal. Okay, and remember, a prime ideal is a proper ideal. So what we're now going to use is taking polynomials modulo an ideal to solve this. Okay, so what I'm now going to consider is I'm firstly just going to try and get rid of one P1. Okay, I'm going to take this step by step. I'm going to try and get rid of just one P1 initially. Okay, and then it's going to generalize and I can do it for all of them. Okay, so I'm just trying to cancel off one P1 from both sides here. Okay, so the way I'm going to consider doing this is I'm going to set up a ring homomorphism from the ring of polynomials over the unique factorization domain R, which everything that I've got here is in, okay? So these are all in that ring of polynomials. P of x is in this ring of polynomials, so P of x times an element of the unique factorization domain will also be in that ring of polynomials. So everything that I've got and I'm working with now is in this ring of polynomials over that unique factorization domain. The fraction field has gone now, we've finished with that. Okay? And I'm going to set up a ring homomorphism from this thing here into R quotiented out by the principal ideal generated by P1 adjoin x. Okay, so of course this is just taking a polynomial modulo this prime ideal generated by P1. Okay, and we've studied this in a previous video on the playlist on ring theory, and we've shown that this is always a ring homomorphism. Whenever you take a ring and quotient it out by a ideal, a proper ideal in this way, you can always establish a very natural homomorphism in this way. Okay, now, so why is this such an ingenious thing to do? Well, firstly, note that because this is a prime ideal, so because the principal ideal generated by P1 is a prime ideal, we can conclude that this unique factorization domain, capital R, quotiented out by this principal ideal generated by P1 is an integral domain. Okay, so I can conclude that this thing is an integral domain, and the reason is that whenever you take a non-zero commutative ring and quotient it out by a prime ideal, you always end up with an integral domain. Okay? And it being an integral domain means that when you generate the ring of polynomials over that quotient ring, you will end up with an integral domain, which is going to be important in a moment. Okay, now let's consider acting this ring homomorphism on both sides of this equation. Okay, so when we take phi of the thing on the left here, what are we going to end up with? Well, look, this polynomial is multiplied by a p1, at least one p1 here. Okay, so that means that all of the coefficients in this polynomial, all of the coefficients in front of the powers of x in this polynomial after it's been multiplied by this, are going to have a power of p1 in. Okay, and that means that they're all going to be reduced to 0 because, of course, in the principal ideal generated by p1, all multiples of p1 are going to be taken on to being equivalent to 0. Okay, so that means that this entire polynomial here is going to be reduced to being the 0 polynomial. Okay, so when we take phi of the left-hand side, we're going to get the 0 polynomial. Okay, now, because this is a ring homomorphism, on the right-hand side, what we're going to get is phi of a of x here, multiplied by phi of b of x, like so. Okay, and now, because this is an integral domain, and you understand now why it's so important that this is an integral domain, we now have an equation in this ring of polynomials over this quotient ring here, okay, and because this is an integral domain, because the coefficient ring here is an integral domain, we can now conclude that one or both of these must be a 0 polynomial. Okay, so let's say that phi of a of x has to be the 0 polynomial. And what does that actually mean about a of x here? Okay, well, if it was reduced to being the 0 polynomial by this ring homomorphism here, what does that mean about a of x? It meant that all the coefficients of a of x must have been multiples of p1. Okay, because that's the only way that all the coefficients of a of x could have been taken to 0 by this ring homomorphism. The only way is if all of those coefficients had been multiples of p1, then of course they would have all been reduced to 0 by this ring homomorphism. Okay, so what we can now conclude is that a of x, all of its coefficients had p1 in them. They were all multiples of p1. So that means, going back to this, that we could have factored out p1 from a of x. So I could have pulled out a p1 from a of x and got some new polynomials. I could have split a of x down into p1 times, let's say, a prime of x here, where a prime of x is still a polynomial of the same degree. Okay, it's still a polynomial in the ring of polynomials over the unique factorization domain, but now I've pulled this p1 out, and then, because this was an integral domain, this ring of polynomials over the original unique factorization domain was an integral domain because, of course, the unique factorization domain was an integral domain, then I can cancel the p1 from both sides, okay, using the cancellation law that works in an integral domain. Now, I applied that for this single p1 here, but you could have applied it for all of these. All of the powers of p1, so that if you had if you had p1 to the power of 3 here, you do it for all three of them, okay, one by one, and then you do it for all these other irreducibles here. Okay, and it relies on the fact that irreducibles are the same as primes in a unique factorization domain. Okay, so you can get away with this, basically, okay, and therefore you can get rid of all of these irreducibles to certain powers here and just change these polynomials, but not actually change their degree. You don't change their degree, okay, and they remain in the ring of polynomials over the unique factorization domain. So yes, you'll have to change them somewhat, okay, but you won't change the fact that they are still non-constant polynomials, and therefore they cannot be units within the ring of polynomials over the unique factorization domain. Okay, then all you have to do is get rid of the unit, and of course that's got a multiplicative inverse, so you can just take it onto the other side and you're back to case 1. Okay, so what I have now successfully shown you is that you can indeed take this polynomial that's reducible in the fraction field, okay, and find a way of writing it as a product of two polynomials that are not units in the actual ring of polynomials over the unique factorization domain, and therefore it is reducible in the ring of polynomials over the unique factorization domain. And that's the end of the proof of Gauss's lemma. So we'll have a break there, and in the next video what we'll have a look at is a corollary of Gauss's lemma.